Good morning, everybody. So my name is Anis Buselmi, irrigation specialist and precision ag engineer at the National Institute of Field Crops. So my presentation is developing decision support tools for irrigation scheduling in Tunisia using ET from a WAPR platform. So the outline of my presentation will start by presenting the challenges and objectives, materials and methods, and result of comparison and model. So to give you a brief introduction about the Tunisia regularly suffers from a significant climate difference between region and season too. So you can see there is a big change from the north part of Tunisia to the south. We have different climate stage. We go from subhumid to Saharan zone. There is irregularity of precipitation characterizing the Mediterranean climate in Tunisia and also can cause certain deficit years. And this have impact on yields, especially wheat production or cereal production, which present the main crops in Tunisia. So the inter-monthly variability is so high that more than 45%. So those present a challenges in for the agriculture in Tunisia, and there is other challenge is the impact of the climate change. And there is a study present that the projection of the climate in 2050, there is a rise of uh, temperature more than 1.5 degrees Celsius. And you know, when the temperature increase, there is high evaporation, and also the growing stage of crops will change because it depends on the growing degree days. Also, there is a water demand is increasing, water availability is shrinking. There is extreme weather events characterizing the weather in Tunisia, and this is one of the major impact of the climate change. So, according to FAO, the stress index, which is the ratio of water demand and the available water, we are more than 121% in 2017. That means the water demand is more than the water available. So we are in critical condition and with a limited resource. And as you know, the agriculture use 80% of the water. Improve this, we need to focus on irrigation and to improve the irrigation. So this is one of the biggest change. Other thing, the average yield of cereals or wheat crops, it's 3.5 ton per hectare, and it's low in irrigated area. And for the government, is the goal to reach 5 ton per hectare. Other thing, the water productivity is low than zero point 0.9 kilogram per cubic meter at the national level, and this is one of the big issue. It's so low, and with a good research or scheduling, we found we can increase from zero point 0.9 kilogram cubic meter to 2 kilograms cubic meter with a good irrigation scheduling. Other things which present a big challenge is the lack of effective tool for extension agent and farmers. There is no tools that farmers can use it for scheduling their irrigation. They use visual decision. It's their decision for irrigation based on visual because the prices of tools like sensors, those expensive, and also they need a good practice to know how to use those sensors, and there is a lack of extension program on irrigation. So those present big challenges for the agriculture in Tunisia, and This is why we focus to develop something that help farmers and extension, especially on irrigation and how to improve the irrigation system. So our objective is to develop tools easy to use by farmers and extension, and also that meets the need of farmers. Especially these tools should be easy to use by farmers, simple, and also have accurate data. Strengthens also the intervention of extension agents because the recommendation of irrigation need to have something to monitor, especially moisture, and to have tools to take a decision. So this can we want to develop something that help extension agents to take decision for farmers and help them for their irrigation or their scheduling. Also, our objective is to increase the water productivity at the national level, so to increase from zero point 0.9 kilograms per cubic meter to 1.6, and also help manage multiple plots and multiple crops at the same time, especially if these tools can help farmers to manage not just one crop but many crops and also many plots, and even if he is far away from his field, so he can schedule his irrigation. So all those present an objectives for us to develop the tools easier and meet those goals. So we go to the materials and methods. So any irrigation program or is based on the water balance. So we need the weather data is precipitation, evapotranspiration, and temperature. Soil data, especially for irrigation, we need to have an idea about the soil data because from the soil data we can extract the physical characteristic of the soil, and we can determine the available water, and also the crop data as the crop coefficient and also the sowing date. The concept of our tools or methods is collecting first. We should collecting data. So we found that WAPOR is a platform from FAO that provide the evapotranspiration and also they provide precipitation. So we want to compare those data with our local weather station to validate this those data from with our station. After that, after validation, we're using those data because the WAPOR platform is an open source, so we can use API program that can help us to extract data from WAPOR. And then development of the model, designing the app to be easier for farmers to use and with features that help farmers to take a decision. And in the end, is testing the model in the field with real data. So compare it to other methods or other reference methods to estimate the evapotranspiration, and the end is the final validation. So like I said, the model concept is based on the water balance, and from soil data we use it the International Soil Reference and Information Center map that called ISRIC is available on the website and is validated by the Ministry of Agriculture. So we use the soil data from this map as a database of our model to extract the field capacity and wilting point so we can determine the available water. For ET, we collecting data from a WAPOR platform that based on the remote sensing for estimating the evapotranspiration, and we are trying to compare those data on compared to our local station. So this is the platform of WAPOR that we can download daily evapotranspiration ETO, the reference evapotranspiration. So we can choose your points or area as a polygon, and you can make the reference time or period, and you can download all data. So it's daily evapotranspiration. So we download all data of those from Webor compared to our local station. So based, we have five local weather station in Bizerte and Janduba, Kef, Beja, Siena, and different bioclimatic zone. So comparing with WAPOR uh, index like the coefficient of determination, the bias, the root mean square error, the mean square error, the mean absolute error, and Wilmot qualitative index. So we testing all those statistic index to see the quality of the WAPOR ET data. So this is the result of the correlation between WAPOR data. We had good correlation between our local station and with the WAPOR data from different year and different stations. Like for the first station, we have the R square is from zero point 0.9 to 0. 0.8 to zero point 0.9, so it's a good correlation. Also, it's in other station the same thing. So we found a good correlation using the WAPR data. Also, for other statistics index, we have a good result about the quality of WAPR data. So it was interesting uh, how those data so close to our local station, weather station. For rain, it's different story. It's because the rain, the precipitation wasn't correlated to our station. So as you can see, there is a low correlation for daily precipitation. So for precipitation, we don't have a good correlation using WAPOR data, especially for precipitation. So we said that we will not use those data for our model. We will use just our local data. But for ET, we'll use it in our model because it is validated with our local station. So the development, like I said, we use the sorry API program to extract the ET data from WebOro and to put it in our models and to use it for calculating the water balance. So as you can see, this is the concept of our model is we have a server, we put GIS data from soil map, and we extract water data in the server, and after that the model will run through app or the web application. So in the web platform, it will be will be target the extension agent and the researchers because people can play on a different scenario using the website. Uh, for the mobile app, it will be focused or targeted to the farmers, so it will be easier to use and simple use by farmers. So the model output and evaluation. This is the output of our model or app. So this is the homepage, first homepage of the app is called Array, and Array is irrigation reference to enhance yields. And this is how you can connect directly using Gmail account, so you don't need authorization using this app. And few step you can run the app. So I will present a video that explain how to use this app and how to manage your field using this app. The video it will be in Arabic, but the subtitle will be in English.
تطبيقة الري إيري هي آلية جديدة تعتمد على التقنيات الحديثة وتمكن الفلاح والفني من الاحتساب الحيني للاحتياجات النباتية من مياه الري حسب نوعية الزراعة وخصائص الحقل، الاعتماد عن تقنية الاستشعار عن بعد، وذلك بهدف الرفع من مردودية المياه وتجنب الإفراط في الري أو الإجهاد المائي للزراعة. تطبيقة الري متاحة مجانا على بلاي ستور. بعد تنزيل التطبيق على الهاتف الذكي يمكن استخدام التطبيق عن طريق الآب. بعد تسجيل الدخول نمشيو لقائمة الاختيارات، وأول حاجة نختار اللغة عربية أو فرنسية أو إنجليزية، ثم نقوم بإضافة الحقل اللي باش نتابعه بعملية الري. نقوم بتسمية الحقل ثم تحديد الموقع الجغرافي بالضغط على الأيقونة وإضافة موقع الحقل. في المرحلة التالية يتم اختيار الزراعة: قمح أو شعير أو قصيبة أو ذرة أو لف سكري. اختيار طريقة تسيير الري: ري عجزي أو ري كامل، ويتم تحديد طريقة احتساب مراحل النمو قار أو باعتماد المجموع الحراري. يمكن للمستخدم اختيار مصدر بيانات الأمطار، إما من الإدارة العامة للموارد المائية أو من موقع ناسا أو من منصة وابور التابعة لمنظمة الفاو. ثم يحدد موعد البذر من الرزنة، وفي الأخير يتم إضافة الحقل. تقوم تطبيقة الري أوتوماتيكيا باحتساب الموازنة المائية الخاصة بالحقل وعرض رسم بياني مفصل للوضعية المائية في التربة. ولمعرفة الحاجيات المائية اليومية للزراعة نتوجه إلى جدولة الري، حيث يمكن الاطلاع على كميات الأمطار المسجلة وكميات مياه المطلوبة. يقوم المستخدم بإضافة كمية الري التي تم تقديمها للزراعة، وعلى إثرها يقوم التطبيق بتحيين جدولة الري. تمكن التطبيق أيضا من الاطلاع على توقعات الطقس.
So as you can see, it's just few steps that you can put it, run it, the app. It's easier to use, it's free on Play Store. So the farmers or extension, they can download the app using their Gmail account and just run, choose the crops. The crops that we use, it's field crops: wheat, barley, corn, and sugar beet. So those crops is major crops that we use it in our institute. And after that, he will choose the sowing date. So not many questions that can you know limit the use of the app, because farmers, they don't want to ask, they want to use something that asks many questions. So it's easier to use any place in Tunisia that he can run the app, and he can run more than plots in different region. Also, the irrigation, it give you an idea about the rain that you have and how much water you can apply. We compared the model with other sensors, so like capacitance sensors, those volumetric sensors, so accurate sensors. So we compared with our model. We have good results. That's showing in this graph. We are close to what the sensor give us result for the moisture in or the water requirements for the plant. So we have a success results using this app, and give you an idea about those sensors. Those sensors so expensive. So imagine we give something free for farmers that can use it, at least in this those kind of crops. So it's important to use those kind of app to improve their water productivity, more than use a visual decision. So also we have conducted an experimental plots to compare the array model or app compared to the maximal ET equation based on FAO 56, to see the difference between those models and to see how we improved the water productivity. We tested this for different varieties, because those varieties, some varieties is advised for irrigated area, and some varieties not advised for irrigated area. And this table present how much water productivity we increase it. We using array model. We had a result of water productivity close to 2 kilograms per cubic meters. Compared to the maximal ET, the water productivity was 1.5. So we increased the water productivity, and also we used less water and high yield. So we not just increased the productivity, but we increased to use those kind of app, and it was a good result that showing using those tools that help farmer not just to increase their productivity but also to increase their yield. So the next step it will be to introduce other kind of crops and like vegetable crops because we don't use for the first version vegetable crops because we work on field crops. So we'll see other collaboration with some partners to introduce other crops and why not to introduce like trees orchard crops like olive trees or other with a good collaboration or partnership with national at national level